Hello, everyone. It's just about noon on the East Coast. So we're going to actually go ahead and just get started. I know there's a lot of material we want to kind of cover this in this session. Hopefully we can keep it to about an hour. So obviously, just for those of you that don't know me, my name is Dave Eckroad. I am the director for IDEA StatiCa in the US. Along with me today is Andrea Castello. She's one of our product engineers here. She's going to be doing most of the work today. I'll just kind of be doing an introduction. So the topic today is design of steel to concrete connections, including base plates. So obviously, yeah, we have some operations in there that can be very helpful to your projects and kind of working on those types of connections. So next slide. So before we look at the agenda, I just want to kind of have a poll for you to understand kind of how are you designing base plates currently? Yeah, so a couple of different options here. You know, obviously IDEA StatiCa, Excel spreadsheets. Okay, I'm going to close the poll in 5 seconds. Last chance. Okay. So now, if we just kind of look at the results, pretty evenly distributed, kind of what I would have expected. Happy to see that not many of you are using hand calcs to design base plates. About a quarter of you are using IDEA, which is great to hear. Hopefully that number is going to increase after today. And yeah, obviously the most common one is Hilti Profis. The interesting part about that is that when you're using Hilti Profis, you're really using the IDEA engine. We've partnered with Hilti for several years now, and kind of we are the kind of backbone on what Profis is built on. Obviously, they have some different capabilities than we do, but overall, we're kind of sharing some technology there. So I'll go ahead and hide that, and then we can kind of look at the agenda. So Andrea is going to be kind of running through several examples as part of this. So one is going to be kind of modeling examples, kind of when to use the base plate operation versus an anchor grid operation. Go through that on a couple of different examples. Kind of walk through the analysis and code checks for the anchors and the concrete blocks. We'll talk a little bit about how contacts and welds can be simultaneously applied or just a contact, and kind of the reasons why you would do either one of those. We'll touch on some verification studies that the University of Tennessee had done for us on some base plate designs. And then finally, we'll touch on some of the limitations within IDEA. And then finally, we will head over to some Q&A. So with that, I am going to turn it over to Andrea.
All right. Thank you. Right, so we have a lot of information to cover, so let's jump into the webinar. All right. So let's start with the two operations that I will focus on this webinar. Both operations will add a concrete block and anchors to the connection, to the model, right? Base plate operation has all the operations needed to design a base plate. It contains the plate itself, the cut, weld, and the anchorage. All right, so that is the good thing of using base plate operation, that you include all the operations, so you just modify things inside this one operation. Then we have this anchor grid operation. That is, you'll need to select this ball grid operation in IDEA StatiCa, and then you change that option into anchors. So the anchor operation, as the name says, only anchorage is located. But the advantage of using the anchorage independently is that you can locate anchors to whatever plate or member's plate is already modeled in the connection. So these operations can be combined in one model, and I will show you some examples in the software where these are used and some recommendation and tips. So this portion or this part of the webinar will be on the modeling side. Then I'll also talk to you about what is happening behind the scenes when we are allocating concrete block and anchors. And then the other part will be just talking about the code checks that we have in the anchors. Feel free to start typing your questions while I am presenting this, and my colleagues will help me with some questions, and at the end I'll show you in the screen some questions. All right, so these are the 7 practical examples that I have here. The first 3 are using base plate operation. All right, so this is the first one. Let me open the software, well, the model that I have here. So I'll start with this inclined column, and the task is to create a base plate for this inclined column. As you can see, this is a Y-flange column, and then the first step will be to add the base plate operation. Okay, so as you can see, this base plate is being perpendicular to the axis of this column. The angle is 75 degrees, right? And this is being perpendicular. So what I wanted to show in this example is that you can modify the orientation of the base plate. So in this case, it's perpendicular, but you can also select horizontal. So this is what I wanted to use instead of perpendicular. But there are some cases where you need to have that perpendicular to the angle of the member, so that is useful as well. So that is one thing. Then the next thing that I want to show you in this example is normally if you have used base plate operation in IDEA StatiCa, always the location of the anchors and the dimension of the plate is from the member. But one tip that I wanted to show is that you can change the dimensions of the base plate from here. It can be either to profile, that is like the default option, rectangle, and circular shape. Also, this helps you to create a different shape of the plate. Anyway, I'll select rectangle, but the trick is here to modify the coordinate system. Instead of from member, you change it from global. Okay, so all the dimensions for the base plate and for the anchors will be referenced to the center line of the member, and that means it is the center line. Well, that means it is from the node. So let me turn off the load effects over here so you can see the node. The node always is in the 0, 0 position. All right, if you move the member, that will be in reference to the node, but the node you cannot move it. So when you're selecting global coordinate system, that will be always from the node. Okay, so in this case, let me just change the dimensions of that base plate. So the top offset over here is this dimension, so that will be 3.5. okay, and then the bottom will be the same, so you have to follow this bottom and top 3.5. there you go. And then the left side, I want to have 9 inches, and then 12 inches in this side. So you can see here the dimensions from the node. I mean, that is an easier way to give dimensions here. Then let's talk about the location of the anchors. So in this case, you can see also it is referenced from the node. So this is 2 inches lateral and then 2 inches vertical here, right? So the top layer, 2 inches is fine. Then I'll use 7 inches. Sorry, negative 7 inches here. Remember that you can use negative values for locating anchors. And then I want another bolt here, so I'll use the top layer input. I'll place a spacing, sorry, and a space, and then the spacing from that last bolt. So you can see I am using positive, so I want that anchor over here, so I use negative value. Okay, and then for the left layer, or this coordinate will be -1, 4. Oop, that will be positive then. There you go. So again, this is an easy way to locate coordinates from the node. All right, then I want to copy this connection. I'll copy this one. And let's say we want to simulate a lateral wall, because this is a beam that is attached to a lateral wall. So we can also use a base plate operation to do that, but then let me show you how it looks when you add it for the first time. So in this case, it's telling you like the geometry of base plate is not valid. Why? Because the orientation is horizontal. So we can change that to perpendicular, and now you have this base plate perpendicular to that angle. Then you can start modifying this base plate operation. As I said, you have the anchors here, the welds from the member to the base plate. So you can see the weld is just in one side. You can modify it to two sides or CGP weld, right? And then you have all the details for the foundation block, the size of the foundation block and the depth, right? I'll talk later about the shear force transfer and the standoff. But again, I wanted to show you the orientation item over here. Then let's say you have a 45 pitch angle here. All right, let me put this like in a lateral view. And you can also go to the base plate operation and then change it to vertical. All right, so again, orientation will help you to set up the position of the base plate. All right, let me close this one. I won't save it. And let's jump into the second example. So the second example will be, let's say, a round HSS with a square base plate or a rectangular base plate. Again, I am using a base plate operation, all right, and I am selecting a rectangle dimension or a rectangle shape of the base plate. But let's say this this design that you need to delete the corner bolts over here, all right, and the ones that are inside the HSS. So a good way to do this is like using the base plate operation, using the top and left layer inputs over here to locate all the bolts, and then you can always go into editor, okay, and delete anchors from here. Okay, so you can see that these are like gray out, and this has like X and Y coordinates. So you can explode this, and even if you want to modify one coordinate from here, that's valid. Okay, and let's say I'll delete the anchor number 6. I click over delete. And then to see what you're doing in the main model, I always recommend to have this in like in this side of the screen and having the model in the other side, and then use the apply option. So you're seeing what's going on in the main model, right? And then you delete the 7th again, and then I'll delete 1, 4, 9, and 12. So I select this, click over delete, then 9 and delete, right? 4, delete, and 12 and delete. And I need a notch in all the corners, so I can select sub operations over here just as you were modifying a plate. So this will be 3 and 3. Okay, I copy this one, and then the corner is 4, copy, 3, copy, and 2 corner, second corner. All right, then you just apply to see that it's okay, and then click OK, right? Let's say you need to modify again this anchors, and you can see that here the top layer and left layer input is grayed out. You can go again to editor, click over the bolts, and you can restore this. Okay, you click OK, and then you will have the option to modify this again, right? So then you can go here again, and you have all the anchors restored. So, I mean, the editor helps you to create a more custom design within the base plate operation. All right? Okay, now let's go back to the presentation, and then let's talk about the shared lock options that we have in the base plate operation. Okay, so let me bring this here. The model that I am using over here is in our templates. When you open IDEA StatiCa and you go to the base plate templates, you will see this this model there. So you can open IDEA and use it and modify it as needed. All right. Remember that all the templates that are in the initial screen can be modified. You can modify sections, members, profiles, thicknesses, shapes, everything, okay? But you can start from something. All right, so now you can see that the base plate operation is over here. In this base plate operation, the editor was used to create a notch over there, so you can see it there, okay? And the focus of this example is to show you that you can, under the foundation block options, you have this shear force transfer selection. So from there, you're selecting how to transfer the shear force coming from all the members to the concrete block. It can be either by friction from the base plate to the concrete block. It can be by shear log, that's the option that I am selecting, or it can be transferring the shear force by the anchors, and that will be code check as well. Okay, so I am selecting here shear log, and once you select that, you have the option to select whatever profile section you need to input there below that base plate. And in this case, I just select a general plate, all right? So for instance, you can see it over here, okay? And then you have all the options to increase the length, okay? Because here you're just selecting the profile, but then you can increase the length to 5 and then modify the position of the shear log. You can see that I move a little bit, or like half of an inch, so I can go back and put it 0, and then it is in the center line, following the center line of this of this Y flange beam. Okay. All right. You can also rotate the shear log if that is needed, like let's say 10 degrees, so that it's going to be rotated there. Okay. Let me put back this 0. And the other thing is that you can combine this shear log with a mortar joint. So you also have the standoff options. That is direct standoff. That means that the base plate will be standing in the concrete block, and then you have the mortar joint. So that is what I use in this case. So you can combine shear log and mortar joint there. But okay, you have this plate over there, like to handle this force of, this shear force in this direction. But let's say in another load combination, you have a larger shear force in this direction, right? In the analysis, what we are doing is that we are taking this area, this small area, for that coming force. But in the second example that I have here, I create a custom shape for that shear log. So how I can do that? So in this, as you can see, I create like a cruciform shape over here. Look at that. So how I bring that? So I select the plus icon to change the profile section, and then I went to the welded and composed, and I use the general steel cross section. All right. What it does is that it opens the general editor. Let me just open this. And in that general editor, we have a lot of content in our website to show you how to use it. But anyway, I'm going to open it here. So we have this, let's say, application within IDEA StatiCa where you can create your own custom design using more, other profile sections and joining them over here using the coordinates or master points, insert pointer. All right. So that's how I design this, or model this using 3 plates here. All right. And then you can see even like the moments for unit moment application, stresses by unit application of moments, shear forces, and everything. All right. So this is useful for these cases, and also if you have a very specific custom design for a connection, you can also use this. I'll close this one and go back to the main model. Then that is the shape I use, and I use this position of shear log to move around that shape. All right. Then what you will see on the check part here. So when you are designing a base plate, you will see, of course, the anchor checks, concrete block check, and the shear check. In this case, what we do for the calculated shear force or the analyzed shear force is that we calculate a resultant force coming from all the members, and that is being applied in this case to that shear log member. Okay, and we use ACI 349. Okay, and this is coming from the design guide #1. So if you review design guide #1, you will see that they recommend using that portion of the code. Anyway, I know that in the newer version of ACI, they have a portion to design the shear log that is coming. I mean, we are working on that, but for now we are using this code to check the shear log. All right. Okay. So now let's go back to the presentation to jump into the next one. This is the part that I was telling you. This is the part on design guide #1. So here we have the formulas recommended, and these are the formulas that we are using for that. Okay. All right. Let's go back. Let's go to the 4.1. This, for example, is to show you how to combine base plate operations and anchor grid operation. David, do you want to do the poll, or shall I continue with this one, and after we can jump into the next one?
No, let's do. So there's 2 other poll questions that we have.
Okay.
The first one's going to be kind of redundant, but from the first one, but we'll just launch it anyway. So this is just asking if you've used IDEA to design steel to concrete connections previously. Okay, we'll close this in about 5 seconds. Okay, so let me just share that for you. Just to let you guys know, so about half of you have used it, 45% haven't used IDEA to design these types of connections, and 5% didn't know that IDEA could do it. So that's so hopefully now you'll be more likely to kind of jump into it and use it in the future. And then the last question that we have is, here we go, I'll launch that one. So how often do you need to design steel to concrete connections, except for besides base plates? So typically like a beam to column wall, or beam to concrete wall, that type of connection, or something other than a base plate that would be a steel to concrete connection. Okay, so we're going to go ahead and close that. Let me share it for you. So a little surprising that 44% of you say it's rarely that you have to do those types of connections. About 25%. So the vast majority don't have to do those connections. Less than 50% of the time. So thank you for the information. It's helpful for us to just kind of understand how things are progressing. But with that, we will get back to the presentation.
All right, thank you, David. So, okay, so this is the 4 example that I have for you. So this is an example to show you how to combine base plate and an anchor grid operation. Why will I do that? So I have this example here, or this, let's say, rough drawing. This is a base plate drawing from, for a tower pole. All right, and normally for those details, you get the radius or the diameter of the position of the anchors, right, and the angle spacing that you need for those anchors, right? So this is a case where the approach is to use the base plate and then using the grid operation. Let me show you why. So let's say you come here. Let me just show you, rotate this. You model the pole, and then you add a base plate operation over there, okay? And then you say, okay, I have to put these 2 anchors over here. I'll use the top layer and left layer input, but then I go to editor, I go into the editor, add the chamfer, because I use the chamfer here to add it in all the 4 corners. And then what I will need to do is to delete all these ones, and then I believe it's a lot of work, and then finding the correct coordinate to locate those two. So the approach, or well, the workaround for this one is to delete the anchors within the base plate operation, and that is just selecting the coordinates there and then deleting the top layer and left layer input there, okay? And then adding an anchor operation. How you add an anchor operation? You use this ball grid or contact thing there, and you change that into anchors, okay? You change the fastener type to anchors. Then how many items I want to connect to the concrete block is just one, and the item one is base plate BP1, all right? Then you modify the type of anchors that you want to use there, okay? But you can see that there is a new concrete block inside there. So the option to use only one block is scrolling down over here and look, find the foundation block option. Then you click over existing block, and that will be using the existing block coming from base plate operation number 1. All right. So now it is time to locate the anchors. From here, you can select the coordinate system. This is why I am using this new grid operation, because you can input that those anchors in a polar coordinate system. You can set up the radius over here, and then selecting the spacing using angles and angle degrees. Okay, so for that one will be 23. Okay, and then let me delete all the angles over here, and you can see if I put 0, that will start in the 0 degrees angle from center line, right? And then if I place 38 and then 14, so the first one will be located at 38 degrees, and then this from the last one, the next one will be at 14 degrees, all right? So that is how you input the anchors in a polar system. After that, you can also use a semicolon over here, so that will start over. So the next group of anchors, it is at 128 degrees, all right? And then the next one is at 14 degrees. And then I am starting over, and so on, all right? In this slide, you can see the graphical explanation of how to input the polar position of anchors. So again, you select the coordinate system as polar, then you specify the radius, and finally you input the spacing using angles, right? So the first one in this case is at 45 degrees, and then the next two anchors are located between 20 degrees between them, all right? So now let's jump into the next example. There you are. Okay. So let's say you want you have this beam, and this beam is seated in an angle, all right? And then that angle needs to be anchored to the to a lateral wall, all right? So here I have the member M1, and the approach for this connection is to model an stiffening member operation, okay? So that stiffening member operation is modeled as a doubler from member 1, okay? So you can see it is exactly down here in the bottom flange, and welded as well because it includes the weld. Look at that. And the next thing will be to add the grid operation. So you come here, select grid operation. You just want to connect one item. Select anchors and then one item. And the first item is a member plate, okay? SM1, let's see, is web 1. All right. Then the next thing to modify is to what is going to be related the foundation block or the concrete block. So you can select plate of member again, and then that will be SM1, stiffening member, and is the web 1. Plate of member, web 1, okay? With these two buttons here, you can select either if it's in one side or the other side, right? So look at this. And then again, you start over locating the anchors in this plate and in the concrete block. I have that prepared already. So again, you can create shear lugs there. All right. All right. The next example is to show you how to use 2 grid operations or more if needed. All right. In this case, this is a end of a truss that needed to be connected to lateral wall. Okay. And then I followed the same approach, modeling stiffening members, okay, and using or modeling them as a doubler, okay. And here you can see that the first grid operation is for this plate, and then the second, as I showed you before, you can anchorage to an existing block, okay. So then you can create 2 groups of anchors. But what happens when you run the analysis and then you get this red cross in the anchors, but the anchors are okay. So if you go here into the check tab, and then you go into the anchors check, you will see that the utilization ratio it's okay, but you have that red cross. If you open that calculation, you can see this warning. So we are telling you, or we are showing this warning because anchors in a different base plate and that interacts, the 2 groups of anchors are interacting in just one concrete block is not covered by the standards. So I mean, we are just showing you this because, I mean, we are doing the code check for the tensile resistance, the shear resistance, but we are not checking the concrete breakout on that concrete block, all right? Just because we don't have a way to let's say, code check this because it is not covered in the different codes that we are following, all right? Just for your information. That's why we're showing that red cross status. All right. Finally, in this file, I have this third example, the same approach, member, vertical member, stiffening members, and you can see that you can put the concrete block wherever you need it. So in this case, this is on this plate, and this is a way to, let me go back to the design tab so you can see it. This is a way to design a hanger or vertical hanger, right? There is no limitation where to locate that concrete block. All right. Let's jump into the next one. This is a steel cable anchorage. That's something we have been asked in the past, how to model this type of anchorage. So again, I am using a grid anchor operation using a plate instead of a member plate, as I showed it before. But one interesting thing from this model is that I am using a rod element. Okay, so if you go into this plus icon to modify the member, you can see that we have this rod shape. Okay, important. The rod element can be only used either with gusset plate operation or connecting plate operation. That's the only options you have for rod element. This is just because we cannot mesh this element. It is treated as a beam element, but there is no way like to mesh like if I am using a plate or a regular profile shape. all right? That's why I wanted to show you this in this example. Anyway, if I go to the grid operation, in this case, I select item 1, SP1, and this is just an stiffening plate. And also, this allows me to explain you that you can use whatever shape you need for your base plate. You can use a stiffening plate and follow the same approach as in this example. You model the stiffening plate using this operation, and then you use the grid operation to locate your anchors, all right? And remember that within the stiffening plate operation, you can select the shape polygon, and then you can bring a DXF to create a custom shape of a plate. Okay? All right. Partially supported base plate. I saw already the question over there, how to manipulate the dimensions of the concrete block, okay? And also I am using here a members plate within the anchor grid operation. So let me open that one, okay? So this is the case where we have this column and this beam. These two are modeled as members, okay? And I use cut of member, okay, to locate the welds there, and stiffener operation. Then the next thing will be to add a grid operation. So that grid operation is attached to M2 bottom flange, all right? But this model or this example just have support until here, right? So to add different offsets to each of the base plate edges to the concrete block, you can scroll down here in until offset, and then when you input only one value, that will be constant for all the base plate edges to the concrete block. Then if you want to model something like this concrete block that we have here, you can input either 2 or 4 dimensions. If you input 2 values, the first value is left and right offsets. Then the second value will be for top and bottom offset. All right, so let me bring this slide so you can understand from this screenshot over here. Okay. If you input 4 values like in this example, you can see here the 4 values. Those are related to left, right, top, and bottom, right? So that is how I model this custom size concrete block. Again, if you hover the mouse over offset, you will see the instructions over here and how the direction of this input is determined by the Y local axis, all right? And in this case, the base plate is the bottom flange of the beam, but then if you have a regular base plate, a rectangular, then it's easier to specify the offsets. All right, then if you run the analysis, let me run the analysis over here. Okay, and then you go into the check tab. You can see the concrete block and the stresses in the concrete, okay? So the concrete block is the white area. That's the offsets we create for this concrete block. And then you can see the loaded area by that beam. And of course, the form shape over here. Then if I increase the scale, you can see how this is the form because the end of the concrete block is over here, right? And of course by the forces of the anchors over there. All right, so that is an example of using a member, but in this case I use also a stiffening member because this was supported by the concrete block, the full part. And then in this case, a plate was used as well. So there are many different options to do these models over here. this type of models. All right. All right, so that was the last example. Okay, so let me go through some slides that I have here. So what is happening behind the scenes? As I showed you before, okay, when you go into the results, you will see like this square only. You're not seeing the 3D view as if you were in the modeling part. So while using CVFEM, that it's the method that IDEA StatiCa uses, it is convenient to simplify the concrete block as a 2D contact element. The connection between the concrete and the base plate resists only compression, okay? And the compression is transferred via the Winkler subsoil model, representing the formations of the concrete block. So let's imagine that we have here some springs, okay, between the base plate and the concrete block, all right? And this springs only allows compression forces, okay? So that is how it works. These are the known Winkler springs, right? And the tension force between the base plate and the concrete block is transferred by the anchor bolts, all right? And the shear force can be transferred by friction, shear lug, or anchors. So this is important that you know that we simulate this as a 2D contact element only. It is not a 3D element within IDEA StatiCa. All right, so let's talk about the tension, what is happening behind the scenes. As I said, anchors are modeled as springs, okay? So then we capture the tension force within the anchors, and then if you select to transfer the shear force via anchors, we also do that, and then we co-check those using the tension and the anchors calculated in the FEA, okay? If you select a gap, the gap portion, as you can see here, and this is the length used, okay? This portion of the anchor is analyzed as a beam element, and then it is co-checked as also beam element by AISC. I can show you in the results how that is analyzed, okay? When selecting gap, the shear is transferred through anchors. There are no options like transferring through shear lug as well, or friction, of course. It is, when you select gap, shear is transferred by anchors, okay? And then when selecting mortar joint, as you can see here, the standoff option, the steel strength in shear is reduced by 0.8 by the co-check ACI. Okay, well, by the co-check within ACI. Okay. Then talking about shear force. The shear force, as I mentioned before, is calculated as resultant of all the applied loads. And then the shear force can be transferred by friction, shear lug, and anchors. Then I won't go through all, the co-checks because I won't have enough time. But these are some articles that will help you to understand what we do in the analysis portion and then in the design when we do the code checks for anchors and concrete block. So this presentation will be available in the same website where you register for this presentation, and you will have the links. Or if you just type these titles there in our website, you can get it. All right. One important thing is that you can overpass or turn off the concrete breakout resistance, okay? If you go into code setup, you can go, you can go to this option that says concrete breakout resistance and ask the software to just calculate that for tension or just for shear or none of those. If you select none of those, then it is telling you the supplementary reinforcement should resist certain amount of of tension and the shear forces that supplementary reinforcement that it's required by ACI. And then you can use those, well, that information to design your reinforcement there. Okay, so if you see the ACI chapter 17, you can see that you can use supplementary reinforcement, and then you can overpass the concrete breakout resistance. So that's why we have this option to overpass that. All right, this is a question that we have that, well, I got in the past. So this user was asking, if I am force milling off the column end, is there any option in IDEA StatiCa to account for this? So the weld size between the end cap and the column can be reduced. So that was added like 1 year ago. You can have the base plate operation, and then you can add a contact between the column and the base plate. So that will reduce the force that the weld is taking from just the contact from column to the base plate. So if you go into results, well, that was the solution, like adding a contact operation that is under weld operation, okay? And here you can see the results without that contact, okay? So look at the maximum stresses, we have 23. With the contact operation, the stresses were reduced by 12 kci, all right? So also, if you add an extra contact, let's say, or an extra contact operation, you will see this like arrow over here, right? But it is important that you know that this needs to be specified in the construction stage, all right? To have that real contact between the member and the base plate. Finally, let's talk about the verification study that the University of Tennessee have done with base plates. And well, this is a comparison between results from CBFEM from IDEA StatiCa and traditional calculation methods used in the US practice for base plate connections. And in this study, you can read that in our website as well. In this study, 3 loading conditions were evaluated: concentric axial compressive load, shear load, and combined axial compressive load and moment loads. All right. This was done by Mark Denavit, professor in the University of Tennessee. Okay, so you can find this in our website. As mentioned before, or not in this webinar, but maybe you have heard this, IDEA StatiCa calculates the real stresses on the plate. And differently from manual calculation, base plates are not totally rigid, and the formation depends on the real stiffness of the plates. Of course, that stiffness depends on the thickness and material, right? So in this study, one of the key findings was that for thick base plates, we have better correlation with the calculations presented in AISC Design Guide number 1. However, when we are analyzing thinner base plates, and you can see here this graph, we don't have the same results because the method used in Design Guide number 1, it is with the assumption that this is a rigid base plate. All right. So this is, I mean, we just needed to prove it by the professor, but this is something that you can feel, right, when you're designing the base plate. For thinner base plates, as I said, results from the traditional calculations and IDEA StatiCa differ significantly, because again, we are getting the real stiffness of the base plate. All right. So that's why we have different results over there. Then one other key finding here in this study is that IDEA StatiCa correctly calculates the shear strength of anchor rods, but it neglects the potential reduction in shear strength due to bending of the anchor rod within the base plate that can occur with certain base plate configurations. For instance, base plate with welded plate washers. So we are not accounting for that extra bending that you have between that washer, that welded washer in the base plate. So that's why it can defer your calculation from manual calculations, okay? With that being said, here I have some limitations that can be sound like limitations, but we are working on those to have better results and well, to implement some things into the software. So as mentioned, plate washer welded to the base plates are not are not possible in the software, so you cannot account for that reduction in the shear for the anchors. Changing resistance factors for specific anchors or code checks are not allowed. So we are using just one factor for anchors, one reduction factor for tension and one reduction factor for shear. So that can be a drawback from some calculations where in the code is being used for some code checks one factor for tension and in the other code check another factor for tension. So you cannot specify different factors for the different anchors, okay? But you can modify those in the code setup if needed, okay? We cannot add welded bolts in the base plate and embed plates. So that's something we're working on because it's it is requested normally, right? But we don't have it, so we cannot do that. And also because we are not doing the 3D model of the concrete block. Finally, if you want to compare anchors from anchors code checks and anchors calculations from Hilti Profis versus IDEA StatiCa, you won't get the exact same values. Why? This is just because anchors in Profis have the real stiffness from their test. Of course, they have their own anchors, their own products, so they have the real stiffness. So that's the real stiffness used in Profis. Okay, so if you compare those, you won't see the same results. Okay, so that's it. Sorry for.
Thanks, Andrea. I know we've gone a little bit past the time.
Mm-hmm.
Obviously, we respect everybody's time. So if you need to drop off, feel free to drop off. We will take a couple minutes and just review some of the questions that we had. So I will, Andrea, unless you had something else.
No, that's it.
Okay. So I'll actually hand it off to Jason, who's our Western Regional Engineer based in the Denver area, and he can kind of go through some of the questions.
Sounds good. Thanks, Dave. Yeah, since we're short on time today, we'll just hit a few here, but we had lots of good questions come in today. One of the first ones had to do with friction and the coefficient of friction. So the question was, when transferring shear forces via friction, what is the assumed coefficient of friction and how do we change it?
Sorry, I was on mute.
Okay.
Yeah, so you can go into the code setup, and then when you are here in the concrete block, you can change that friction coefficient.
So that can be changed to whatever we like, right?
Mm-hmm.
Perfect. There were a few questions regarding ACI 349 versus ACI 318. Can you just kind of hit on that again with what you were saying and sort of updates to the 318?
Yeah, so as I said, in the ACI 318 version 2019, there is a new portion to review the shear log. So we're working on that to add ACI version 2019. But if you look at design guide number 1, that code that I mentioned, the 349, is being used. All right. So that's why we're using that ACI 349.
And that's just in regard to the shear lugs, correct?
Exactly. Yeah. Sorry. Yeah.
Everything else is per ACI 318.
Exactly.
Yeah. Okay. Somebody was kind of asking about recommendations for when they want to use mechanical or adhesive anchors. So I thought it might be worth mentioning sort of the Hilti integration that we're working on, and anything else you'd recommend for that process.
Yeah. I won't say a time frame because I'm not sure about it, but at some point we'll be able to transfer the information from Hilti to IDEA StatiCa to bring those specific details that you need for the anchors.
Perfect. And so at this point, if I wanted to use mechanical anchor, I'd run my design in here for a base plate and then design my anchor in a different software using the forces I came up with.
I believe I'll need to check on that one. Yeah.
Okay.
Yeah. And then let me just jump into this about the ACI 318. Maybe it was just a confusion. I was talking about the ACI 349 just because I was talking about the shear log, but anchors are designed using ACI 318, chapter 17. So let me bring this here. So when you go over here, you can see all the checks: anchor tensile resistance, shear resistance, pry out, and then everything is based on ACI. Let me just open this one that I have here to show you what happens when you also add a gap, so you can see how that is checked. Give me one sec. But everything is analyzed with ACI 318 for the anchors. Sorry if it was a confusion because I was mentioning about shear log.
Right.
Yeah.
Perfect. Okay, that sounds good.
Go ahead with the next one. Sorry.
Sure. There was another question or sort of comment about someone had found the anchor bending calculation to be a little conservative. And so I just wanted to clarify that our calculation was updated just recently, I think, to sort of accommodate different scenarios of bending. Is that right?
Yeah, so that's what I wanted to show. So if you change it to gap option here, I have 2 inches gap, and then you calculate this. In the past, what we were just calculating in a linear way, like just taking the length and calculating the moment with that length, and that's it, right? The force and then the length and just a manual calculation. But now, if you go into the check tab, we are calculating that by FEA. And as I mentioned, we are treating this portion of the anchor, this small portion of the anchor, as a beam element. So if you go into the anchors, you can see here what happens when you add a gap. So you get the tension forces, shear forces, and bending moment in that bolt, in that portion, in that bolt. All right. And if you click over here, then stand-off anchor tensile resistance, and then the shear resistance. So as you can see, this formula is just like if we were calculating a beam resistance. Okay. Stand-off anchor bending resistance. So that is the compare against the moment. But again, ACI over here, AISC for the bending part. Okay.
Sounds good. I think we have time maybe for just one more here. Somebody else was asking about recommendations for the forces in option and how to think about that with base plates. Do you have any thoughts or guidance on that?
I'll say base plates. it's okay. If you place forces in node, it's fine, because that is just like a cantilever beam. And the base plate is always located over here in the node position. Okay, so forces in node will be fine. And model type, well, that's depending on the member. Let me see if I can answer one more. Okay. Can it handle a circular concrete pedestal? We have heard that. I should put it there, that in the limitations we cannot. Sorry.
Andre, I guess the last question
Yeah.
that I would say we cover is just I know there are multiple questions about the implementation of ACI 31819 for base plates. Do you have an update on that?
You know that we don't like to say timeframes, but
yeah, we get ourselves in trouble when we give an exact time frame.
Yeah, but if you ask me, I believe that will be in the next year.
Yeah, that's what I understood.
Yeah.
Was basically for version 24, which would be April of next year. I know we actually had I responded with that, and somebody was asking if we can push it up, so we can kind of push on it a little bit on our side to kind of see what happens. But all right, I think we've gone about almost 15 minutes past. So like I said, we do want to respect everybody's time. All these questions will be responded to, and we can also kind of include them on the webinar page. So with that, I appreciate everybody sticking in with us here. I think it was a great presentation. I know there was a lot of information to cover. So definitely, as you have questions, feel free to reach out to IDEA. Through the user portal is the best way to kind of submit a case or question. And with that, enjoy the rest of your day. Thank you very much.